Light, in the perfect vacuum of space, travels at exactly 299,792,458 meters per second. Not approximately this speed, not close to this speed, but precisely this speed, every single time, without exception. This number has been measured with extraordinary precision, refined through countless experiments, and verified across every conceivable circumstance. What makes this fact truly remarkable, what elevates it from mere scientific curiosity to one of the most profound discoveries in human history, is that this speed remains absolutely constant, regardless of who measures it or how they are moving. Whether you stand perfectly still on Earth's surface, hurtle through space in a rocket at tremendous velocity, or somehow manage to travel at 99% of light speed yourself, if you measure the speed of a passing light beam, you will always, without fail, get the same answer: 299,792,458 meters per second. And if you want to know the real reason behind it, then watch this video till the end and subscribe to the channel. Let's begin. To our everyday intuitions, this seems impossible, even absurd. Our entire lived experience screams against this reality. When you stand on a train platform and watch a train rush past at 60 miles per hour, then walk alongside the platform at 3 miles per hour in the same direction as the train, the train appears to be moving away from you at only 57 miles per hour, relative to your motion. This is the common sense of velocity addition that we experience every moment of our lives. If you throw a ball forward from a moving car, the ball's speed relative to the ground is the sum of the car's speed and your throwing speed. This is so obvious, so fundamental to our understanding of motion, that it seems like a basic truth about how the universe must work. Everything in our daily experience confirms this additive property of velocities. When two cars approach each other from opposite directions, each traveling at 50 miles per hour, they close the distance between them at 100 miles per hour. This is not complicated mathematics. This is simple arithmetic that children can understand and predict. Yet light refuses to obey these intuitive rules. If you stand still and measure a beam of light passing by, you get 299,792,458 meters per second. Now imagine you board a spaceship capable of traveling at half the speed of light, an astounding 149,896,229 meters per second, and you chase after that same light beam. Common sense insists that the light should now appear to be moving away from you at only half its original speed, since you're moving at half light speed in the same direction. Your everyday experience with trains and cars and thrown balls demands this outcome. But nature does not care about our intuitions. When you measure that light beam from your impossibly fast spaceship, you still get exactly 299,792,458 meters per second. The light is not moving away from you any slower than it was when you stood still. This defies everything we think we know about motion, about relative velocities, about the basic structure of space and time. This is not a small anomaly or a minor correction to our understanding. This is a fundamental contradiction with the entire framework through which we perceive reality. If light speed is constant for all observers, then something else must be variable. Something we thought was fixed and absolute must actually be flexible and relative. The implications of this single fact cascade through physics, like dominoes falling in an intricate pattern, forcing us to rebuild our understanding of the universe from the ground up. Time itself cannot be absolute and universal. Space cannot be rigid and unchanging. The familiar three-dimensional space and one-dimensional time of our experience must be replaced with something more subtle, more interconnected, and far stranger than anything our ancestors could have imagined. All of this, the entire restructuring of our cosmic understanding, flows from the simple, stubborn, experimentally verified fact that light speed is constant. For most of human history, this puzzle did not exist because light was not understood as a wave phenomenon with a measurable speed. Ancient philosophers debated whether light traveled instantaneously or took time to move from place to place, but they had no way to measure such things. Even when it became clear that light had a finite speed, determined first through astronomical observations of Jupiter's moons by Ole Rømer in 1676, the full implications of this discovery remained hidden. The speed was simply a number, a property of light, nothing more mysterious than the speed of sound in air or the rate at which water flows downhill. But as the 19th century progressed and physicists developed increasingly sophisticated theories about the nature of light, a puzzle began to emerge that would ultimately revolutionize our entire understanding of reality. The scientists of the 19th century were extraordinarily successful at understanding waves. They had mastered the mathematics of sound waves traveling through air, water waves rippling across oceans, and vibrations traveling through solid materials. In every single case, these waves required a medium, some physical substance that actually did the waving. Sound cannot travel through a vacuum because sound is literally the vibration of air molecules, or the molecules of some other material substance. Remove the material, and sound cannot exist. Ocean waves are water molecules, oscillating up and down as energy passes through the liquid. Vibrations in a metal bar are the atoms of that metal moving in coordinated patterns. This principle seemed universal. Waves require a medium. When James Clerk Maxwell published his equations describing electricity and magnetism in the 1860s, he made a stunning discovery that emerged from the mathematical structure itself. His equations predicted that oscillating electric and magnetic fields should produce waves that propagate through space, and when he calculated the speed of these electromagnetic waves, he got a number that matched the known speed of light. This was too much of a coincidence to ignore. Maxwell and his contemporaries concluded that light must be an electromagnetic wave, a triumph of theoretical physics that unified previously separate phenomena into a single elegant framework. But this triumph brought with it a deep problem. If light is a wave, what medium is doing the waving? The physicists of that era approached this question with perfect logical consistency based on everything they knew about waves. Light travels through empty space. We can see stars millions of light years away across the vacuum of the cosmos. Therefore, they reasoned, what appears to be empty space must actually be filled with some incredibly tenuous substance, so rarefied that we cannot detect it directly, yet capable of transmitting vibrations at the enormous speed of light. They called this hypothetical substance the luminiferous ether. The name itself reveals their thinking. Luminiferous meaning light-bearing, and ether being an ancient term for the pure, clear, celestial substance thought to fill the heavens. This ether would have to possess remarkable properties. It had to be rigid enough to support waves traveling at 300,000 kilometers per second, yet offer no detectable resistance to the motion of planets, stars, and indeed the Earth itself as it orbits the Sun. It had to permeate all of space, filling the universe completely, yet remain invisible and intangible to every direct measurement. Despite these seemingly contradictory requirements, the ether hypothesis made sense within the framework of 19th century physics. Every other wave had a medium, so light must have one too. The strange properties required of the ether were simply a reflection of how special and unusual electromagnetic phenomena were compared to everyday mechanical waves. Many brilliant physicists worked to develop detailed models of the ether, trying to understand its mechanical properties, how it could support electromagnetic oscillations, and how it related to ordinary matter. The ether became a central concept in physics, and detecting it, proving its existence through direct measurement, became one of the most important experimental challenges of the age. If the ether truly filled all of space, and if Earth moved through this ether as it orbited the Sun, then there should be an ether wind blowing past Earth, just as you feel wind on your face when you drive a car with the windows down. Even on a perfectly calm day, the motion of the car through stationary air creates relative wind. And likewise, Earth's motion through stationary ether should create a detectable effect. This is where the Michelson-Morley experiment enters the story, an experiment so important that it has been called the most famous failed experiment in the history of science. Albert Michelson and Edward Morley were not trying to overthrow the foundations of physics or discover something revolutionary. They were trying to do what seemed like straightforward, careful experimental work: detect and measure Earth's motion through the luminiferous ether. Their reasoning was impeccable. Earth orbits the Sun at approximately 30 kilometers per second. If the ether exists and is stationary, or at least not moving at exactly Earth's orbital velocity, then Earth must be moving through it. This motion should affect the speed at which light travels. Relative to Earth's surface, light traveling in the same direction as Earth's motion through the ether should have a different speed relative to Earth than light traveling perpendicular to that motion. Just as a swimmer makes different progress swimming with a current versus swimming across it. To detect this expected difference, Michelson and Morley built an ingenious device called an interferometer. The principle was elegant. Split a beam of light into two perpendicular paths, send each beam bouncing back and forth multiple times to magnify any tiny differences, then recombine them and look for an interference pattern. If light travels at different speeds in different directions relative to the ether, the two beams would become slightly out of phase with each other, creating a characteristic pattern of light and dark bands. The apparatus was built on a massive stone slab floating in a pool of mercury to eliminate vibrations, and it could be rotated to test different orientations relative to Earth's presumed motion through the ether. The sensitivity was extraordinary. It could detect differences far smaller than the effect they expected to see. Michelson and Morley performed their experiment in 1887, measuring carefully, rotating their apparatus, checking and rechecking their results. They expected to see a clear signal of Earth's motion through the ether. Instead, they found nothing. No matter which direction they oriented their interferometer, no matter what time of day or what season of the year they performed their measurements, the speed of light was identical in all directions. The interference pattern showed no shift as they rotated the device. Light appeared to travel at exactly the same speed along every path, as if there were no ether wind at all, as if Earth was somehow stationary in the ether, despite its obvious rapid orbit around the Sun. This was not what you would call a subtle null result that could be explained away by experimental error. The effect they were looking for was large, and their apparatus was sensitive enough to detect a small fraction of it. Yet they found absolutely nothing. Zero effect. A complete null result. The immediate response was puzzlement and various attempts to explain away the results. Perhaps Earth somehow drags the ether along with it. So near Earth's surface there is no ether wind? But this explanation created problems with other observations, particularly the aberration of starlight. which seem to require that the ether not be dragged along. Perhaps the ether has some more complicated behavior, varying with altitude or affected by the mass of Earth in some unforeseen way. Various proposals emerged, each adding complexity to try to save the ether hypothesis. Other physicists proposed even more radical solutions. The Irish physicist George Fitzgerald and the Dutch physicist Hendrik Lorentz independently suggested that objects moving through the ether might physically contract in their direction of motion by exactly the right amount to cancel out the expected effect. This contraction would be a real physical compression of matter, caused by the interaction between the material and the ether. If Michelson and Morley's apparatus contracted just so as it moved through the ether, this would explain why they detected no difference in light speed. This explanation worked mathematically. Lorentz developed detailed equations describing how matter should contract and how time measurements would be affected. But it felt like an ad hoc solution designed specifically to preserve the ether concept. Why would nature conspire to hide the ether's effects in this particular way? The contraction required was precisely calculated to make the ether undetectable, which seemed suspiciously convenient. Into this confusing situation came a young Albert Einstein, working as a patent examiner in Bern, Switzerland. Largely isolated from the mainstream physics community, Einstein had been puzzling over these questions since he was 16 years old, thinking deeply about the nature of light and motion. He asked himself a simple question that cut to the heart of the matter. What would happen if you could ride alongside a light wave, moving at the speed of light yourself? According to Maxwell's equations, light is an oscillating electromagnetic wave, with electric and magnetic fields rising and falling in a coordinated dance as the wave propagates through space. But if you traveled at light speed alongside the wave, you would be at rest relative to the oscillating fields. You would see a static electromagnetic field pattern, frozen in space, oscillating in time, but not propagating. This, Einstein realized, was a contradiction. Maxwell's equations do not predict static, non-propagating electromagnetic field patterns of this type. The mathematics simply does not allow for such a thing to exist. Either Maxwell's equations were wrong, or the premise of the thought experiment was wrong. You cannot actually travel at the speed of light alongside a light wave. Einstein grappled with this puzzle for years, approaching it from different angles, trying to understand what assumption in the usual picture was mistaken. The key insight came when he stopped trying to preserve the concept of absolute time and absolute space, stopped trying to save the ether, and instead asked what would happen if he took the constancy of light speed as a fundamental postulate, a basic assumption from which everything else would follow. In 1905, Einstein published a paper titled On the Electrodynamics of Moving Bodies that would change physics forever. The paper began not with complicated mathematics or detailed experimental analysis, but with two simple postulates, two fundamental assumptions that Einstein would use to rebuild our understanding of space, time, and motion from the ground up. The first postulate was the principle of relativity. The laws of physics are the same in all inertial reference frames. An inertial reference frame is simply a perspective, a coordinate system, in which objects not subjected to forces move in straight lines at constant speeds. If you're floating in deep space far from any gravitational influences, you're in an inertial frame. If you're in a smoothly moving train traveling at constant velocity, you're in an inertial frame. Einstein's first postulate says that physics looks the same in all such frames. There is no privileged frame, no absolute rest, no way to determine through any physical experiment that you are the one truly at rest while others are moving. This principle actually goes back to Galileo, who noted that if you're below deck on a smoothly sailing ship, you cannot tell through any mechanical experiment whether the ship is moving or stationary. Einstein extended this to all physical laws, not just mechanics. The second postulate was the revolutionary one. The speed of light in vacuum is the same for all observers in inertial frames, regardless of the motion of the light source or the observer. This is the constancy of light speed, stated as a fundamental principle of nature. Einstein did not try to explain why this was true or derive it from some deeper principle. He simply asserted it as a basic fact about the universe, suggested by the Michelson-Morley experiment and the structure of Maxwell's equations, and then worked out the consequences. This postulate immediately eliminates the need for the ether. If light speed is constant for all observers independent of their motion, then there is no absolute rest frame defined by an ether medium. The ether becomes superfluous, unnecessary baggage that the theory no longer requires. What makes these postulates profound is how they resolve the apparent paradoxes. If light speed is constant for all observers, then the usual rules of velocity addition cannot apply to light. When you board that spaceship traveling at half light speed and measure a light beam, you must get the full speed of light, not a reduced speed. But for this to be true, something else must give. Einstein worked through the mathematics and discovered that both time measurements and space measurements must vary between observers in different states of motion. Time itself is not absolute and universal. Space itself is not rigid and fixed. The flowing of time and the extension of space must adjust themselves for observers in relative motion so that everyone measures the same speed for light. This was a conceptual revolution of staggering proportions. To truly understand what constant for all observers means, we need to examine it carefully and probe its implications. Imagine you are floating in space, at rest relative to the distant stars, and a beam of light passes by you. You measure its speed using whatever instruments you like. Laser timing devices, careful measurements of distance and time, anything you can imagine. And you get 299,792,458 meters per second. Now imagine your friend is in a spaceship traveling past you at half the speed of light, moving in the same direction as the light beam. You might expect your friend to measure the light traveling away from them more slowly, since they are chasing after it at tremendous speed. But when your friend actually performs the measurement using identical instruments, they get exactly the same answer: 299,792,458 meters per second. The light is not moving away from them any slower than it was moving away from you. Now add another complication. Imagine a third observer in another spaceship traveling at half light speed in the opposite direction from the first spaceship. This third observer is moving away from the light beam, so you might expect them to measure the light catching up to them at greater than the standard light speed. The light speed plus the observer's speed away from it. But again, when this third observer measures the light beam's speed, they get 299,792,458 meters per second, identical to what you and the first spaceship observer measured. The light is not catching up to them any faster. It does not matter what direction anyone is moving, how fast they are going, or any other detail of their motion. Every observer in every inertial reference frame measures the same speed for light in vacuum. This is not an approximation or a limit case. It is exact, absolute, and universal. This creates an immediate logical problem. If everyone measures the same light speed, but different observers are in relative motion to each other, then they cannot agree on measurements of time and distance. Suppose you and your friend in the fast spaceship both watch the same photon of light travel from point A to point B. You both agree it's the same photon traveling between the same 2 points in space, but you disagree about how far apart points A and B are because you're measuring space from different frames of reference. And since you both must calculate the same speed for the photon, speed being distance divided by time, if you disagree about the distance, you must also disagree about how much time elapsed during the photon's journey. Your friend's clock, moving at half-light speed relative to you, must be ticking at a different rate than your clock. Their meter stick, moving at half-light speed, relative to you, must be measuring distances differently than your meter stick. These are not measurement errors or instrumental artifacts. These are real, fundamental differences in how time passes and how space extends for observers in relative motion. This is time dilation, and it is one of the most counterintuitive predictions of Einstein's theory. Time itself, the steady, universal flow that we experience as the background against which all events unfold, is not universal at all. Different observers moving at different speeds experience time passing at different rates. The mathematics works out such that a clock moving relative to you always appears to tick more slowly than an identical clock, at rest relative to you. This is not because the moving clock is malfunctioning or because of some mechanical effect of motion on the clock mechanism. Time itself genuinely passes more slowly for the moving clock. Every physical process occurring in the frame of the moving clock, chemical reactions, biological aging, radioactive decay, the oscillations of atoms, all of these slow down by exactly the same factor, because time itself is moving more slowly in that frame relative to yours. To see why this must be true, imagine a simple clock made of light, called a light clock. This clock consists of two parallel mirrors separated by a fixed distance, with a photon of light bouncing back and forth between them. Each round trip of the photon between the mirrors represents one tick of the clock. Now, imagine this light clock is at rest relative to you. The photon travels straight up from the bottom mirror to the top mirror, then straight back down, covering a distance of twice the mirror separation. Each tick you can calculate the time per tick. It's twice the mirror separation divided by the speed of light. Now imagine an identical light clock moving past you at high speed, oriented so the mirrors are perpendicular to the direction of motion. From your perspective, as the photon bounces between the mirrors, the clock is also moving sideways. The photon must travel a diagonal path, up and to the side, to where the top mirror has moved by the time the photon gets there, then down and to the side, to where the bottom mirror has moved. This diagonal path is longer than the vertical path the photon takes in the clock's own rest frame. Here is the crucial point. The photon must travel at the speed of light in both frames of reference. That is the whole content of the second postulate. If the photon travels a longer path from your perspective, and it must do so at the same speed it travels in the clock's rest frame, then from your perspective, more time must elapse per tick. The moving clock ticks more slowly than an identical clock at rest relative to you. This is not about the mechanics of this particular clock. It is about time itself. Any clock, any process, any measure of time passing will show the same effect. Time genuinely passes more slowly in moving reference frames, and the factor by which it slows down depends on the velocity according to a precise mathematical formula involving the speed of light. This time, dilation is not reciprocal in a simple way, and this is crucial to understanding. From your perspective, the moving clock ticks slowly. But from the perspective of the person moving with that clock, their clock is at rest and ticking normally. while your clock is moving and therefore ticking slowly, from their perspective. This seems like a contradiction. How can each observer see the other's clock running slow? But it is not actually contradictory because there is no absolute way to compare the clocks unless one of the observers accelerates to match the other's velocity, and acceleration breaks the symmetry of the situation. During purely inertial motion, each observer's measurements in their own frame are correct for that frame, and the apparent contradiction resolves when you carefully account for the relativity of simultaneity. The fact that different observers do not agree on which distant events happen at the same time. Just as time must be flexible to preserve light-speed constancy, so must space. Objects moving at high speeds do not just experience time differently, they also physically contract in the direction of their motion. This is length contraction, and it emerges from the same principles that produce time dilation. Imagine a spaceship passing by you at high speed. From your perspective, measuring the spaceship's length by noting the positions of its front and back end at the same moment. In your reference frame, the spaceship is shorter in the direction of motion than it would be if it were at rest relative to you. This is not an illusion or a perspective effect. The spaceship is genuinely contracted from your frame of reference. Its atoms are closer together in the direction of motion, and any measurement performed within your frame will confirm this contraction. Again, this seems to create a paradox. From the spaceship's perspective, the ship is at rest and at its proper length, while you and everything in your reference frame is moving rapidly past the ship and therefore contracted. How can both perspectives be correct? The resolution again lies in the relativity of simultaneity. When you measure the spaceship's length by marking the positions of its front and back ends at the same time in your frame, those two marking events are not simultaneous in the spaceship's frame. The relativity of simultaneity means that different frames disagree about whether spatially separated events are simultaneous, and this disagreement exactly accounts for the apparent contradictions in length measurements. Each frame's measurements are correct for that frame, and when you carefully work through the transformation between frames, accounting for differences in simultaneity judgments, everything is consistent. The mathematical relationship between the contraction and time dilation is precise and necessary. In fact, they are two aspects of the same fundamental phenomenon, the structure of space-time. This is perhaps Einstein's deepest insight, developed more fully in subsequent years. Space and time are not separate, independent entities. They are unified into a single four-dimensional continuum called space-time. Events in space-time are specified by four coordinates, 3 spatial dimensions and 1 time dimension. The separation between events has both spatial and temporal aspects, and different observers in relative motion will disagree about how much of that separation is spatial and how much is temporal. But they will all agree on a combined quantity called the space-time interval that mixes space and time according to a specific mathematical formula. To understand this unity of space and time, consider that you are always moving through space-time at the speed of light. This sounds strange at first. You might be sitting still right now, not moving through space at all. But you are moving through time, and quite rapidly at that. Every second, you age 1 second, moving 1 second into the future. This motion through time is your velocity through the time dimension of space-time. When you start moving through space, accelerating from rest to some velocity, you must begin allocating some of your space-time velocity to spatial motion. The total space-time velocity remains constant at the speed of light. But now, instead of all of it being temporal motion, some of it becomes spatial motion. The faster you move through space, the more of your space-time velocity is spatial, and correspondingly, the less of it can be temporal. This is why time slows down for moving objects. They are moving through time more slowly because more of their motion through space-time is spatial. Light itself travels through space at the speed of light, which means light uses all of its space-time velocity for spatial motion and has none left over for temporal motion. This is why photons do not experience the passage of time. From the photon's perspective, if we can meaningfully talk about such a perspective, no time elapses between the moment it is emitted and the moment it is absorbed, no matter how far it travels through space from the perspective of other observers. A photon emitted by a star 10 billion light-years away and absorbed by your eye today has, from its own perspective, existed for 0 time. Its entire journey, 10 billion years by Earth's reckoning, is instantaneous from the photon's point of view. This is not some mystical or metaphorical statement. It is a direct consequence of the mathematics of space-time and time dilation. At the speed of light, time dilation becomes infinite and time stops. This observation leads directly to one of the most profound restrictions in physics. Massive objects can never reach the speed of light. To see why, consider what happens as you accelerate. You use energy to increase your velocity, to shift more of your space-time motion from the temporal dimension to the spatial dimensions. At low speeds, this is straightforward. Push on something and it accelerates, gaining kinetic energy proportional to the square of its velocity, according to the classical formula. But as you approach significant fractions of light speed, something changes. The same amount of energy produces less and less increase in velocity. You can keep adding energy, but the velocity increases more and more slowly, asymptotically approaching but never reaching light speed. The reason is that energy and mass are related through Einstein's famous equation E equals mc squared. As you add kinetic energy to an object, you are actually increasing its mass, its resistance to further acceleration. The faster you go, the more massive you become from the perspective of your starting reference frame, and the more energy it takes to accelerate you further. As your velocity approaches light speed, your mass approaches infinity, and the energy required to accelerate you any faster also approaches infinity. To actually reach light speed would require infinite energy, which is impossible. This is not a limitation of technology or engineering. It is a fundamental feature of space-time geometry. Massive particles always move slower than light, and the closer they get to light speed, the more energy they possess, and the harder they become to accelerate further. Only massless particles can travel at light speed, and they must always travel at exactly light speed. They cannot go slower. Photons are massless, which is why they travel at the speed of light. If a particle has any mass at all, even a tiny amount, it cannot reach light speed. If a particle is massless, it must travel at light speed in all reference frames. There is no such thing as a slow photon or a photon at rest. The concept is meaningless within the framework of relativity. Massless particles always move at the universal speed limit, and they experience no passage of time. Their existence, from their own perspective, is instantaneous and eternal simultaneously. A single frozen moment that encompasses their entire journey through space. This leads us to one of the deepest reasons why light speed must be constant and why it must be a universal speed limit. Causality itself depends on it. Causality is the principle that causes precede effects, that events unfold in a logical order where earlier events can influence later events, but not vice versa. This seems so obvious that it is hard to imagine it could be otherwise. But if information could travel faster than light, or if light speed varied for different observers, causality would break down. Events that appear causally ordered to one observer would appear in the reverse order to another observer, with effects preceding their causes. This is not merely counterintuitive, it is logically contradictory. It would mean the universe operates in a fundamentally incoherent way. To see how faster-than-light communication would violate causality, imagine you have a device that can send messages instantaneously across space, arriving at the same moment they are sent regardless of distance. Suppose you send such a message from Earth to a spaceship moving away from Earth at high speed. From Earth's perspective, the message is sent and received simultaneously. But from the spaceship's perspective, due to the relativity of simultaneity, events that are simultaneous in Earth's frame are not simultaneous in the ship's frame. In fact, from the ship's perspective, the message arrives before it was sent. If the ship then sends an instantaneous reply back to Earth, again arriving simultaneously in the ship's frame, this reply can arrive at Earth before the original message was sent, from Earth's perspective. You receive a reply before you send your message, which makes no logical sense. You could receive instructions not to send the message, creating a grandfather paradox where the message prevents its own transmission. The constancy of light speed for all observers prevents this paradox. No matter how fast different observers are moving, they all agree on the speed of light, which means they all agree on the causal structure of space-time. Events connected by light signals have an unambiguous causal ordering that all observers agree on. Events that can be connected by a slower-than-light signal also have an unambiguous causal ordering. Only events so far apart in space and so close together in time that not even light could travel between them have an ambiguous ordering. These are called space-like separated events, and they cannot be causally connected. No signal, no influence, no information can pass between space-like separated events. The speed of light is the speed of causality itself, the maximum rate at which cause and effect can propagate through the universe. This deep connection between light speed and causality hints at something profound. Light speed is not really about light at all. It is a fundamental property of space-time itself. The fact that light happens to travel at this speed is almost incidental. Light travels at this speed because it is massless, and massless particles must travel at the universal speed limit. But the speed limit exists independent of whether light exists. Even in a hypothetical universe with no electromagnetic radiation, no photons, no light at all, the structure of space-time would still contain this maximum speed, this conversion factor between space and time. We call it the speed of light only because light was the first thing we discovered that travels at this fundamental speed. The hint that light speed was something special came even before Einstein's theory, encoded in Maxwell's equations. These equations describe how electric and magnetic fields interact and propagate. They were discovered in the 1860s through careful experimental work and brilliant theoretical synthesis. What is remarkable about these equations is that they contain no variable for the observer's motion. When Maxwell calculated the speed of electromagnetic waves from his equations, he got a specific number determined only by fundamental constants: the permittivity and permeability of free space, quantities that describe how electric and magnetic fields behave in vacuum. This speed came out to approximately 300,000 kilometers per second, matching the known speed of light and confirming that light is an electromagnetic wave. But notice what is missing. Maxwell's equations do not ask, speed relative to what? They give a single answer for the wave speed, independent of how the source is moving or how the observer is moving. This is very different from the wave equation for sound, which predicts different wave speeds, depending on the wind, velocity, and the motion of the source. And observer. Maxwell's equations are the same in all inertial reference frames. They satisfy Einstein's first postulate automatically, and they predict that electromagnetic waves travel at the same speed in all such frames, which is Einstein's second postulate. The invariance of light speed is built into the mathematical structure of electromagnetism. Einstein did not need to add something new to Maxwell's equations. He needed to take them seriously and accept their implications for the nature of space and time. When you dig even deeper into the mathematics, you discover that light speed is more accurately understood as a conversion factor between units of space and units of time. We typically measure space in meters and time in seconds, but these are human conventions. In the equations of relativity, space and time are much more naturally expressed in the same units. If we measure time in seconds, we can measure space in light seconds, the distance light travels in 1 second. In these units, the speed of light is simply 1 light second per second, or just 1. This makes the formulas of relativity much simpler and more elegant. The speed of light disappears from the equations, replaced by pure unity, because we have chosen units where space and time are measured in compatible ways. This might seem like a mathematical trick, but it reveals something deep. The conversion factor between space and time is a fundamental feature of the geometry of space-time. It is like the conversion factor between the x and y axes on a graph. There is no physical conversion factor because they are the same type of thing measured in the same units. Similarly, space and time are not two different types of entities requiring a conversion factor to relate them. They are two aspects of a single unified space-time, and what we call the speed of light is simply the geometric constant that appears when we artificially separate space-time into space and time-time using our conventional units. The constancy of light speed is thus a statement about the geometry of space-time itself, not primarily about the properties of light. This geometric perspective connects to a much older principle in physics, the principle of relativity. Galileo recognized that the laws of mechanics are the same in all reference frames, moving at constant velocity relative to each other. You cannot determine through any mechanical experiment whether you are at rest or moving uniformly. A ball thrown on a smoothly moving ship follows the same parabolic path, obeys the same equations of motion as a ball thrown on shore. This principle worked well for mechanical phenomena, but it seemed to fail for electromagnetic phenomena. Maxwell's equations, as originally understood, seem to define a privileged reference frame, the frame in which the ether is at rest, in which electromagnetic waves propagate at a specific speed in all directions. Einstein's insight was that the principle of relativity should apply to all physics, not just mechanics. If the laws of physics are truly the same in all inertial frames, and if Maxwell's equations are correct laws of physics, then they must have the same form in all frames. This requires that electromagnetic wave speed be the same in all frames, which in turn requires the radical restructuring of our concepts of space and time that Einstein discovered. The constancy of light speed is thus the bridge that makes it possible to extend the principle of relativity to encompass all physical phenomena, including electromagnetism. It is what makes the universe logically consistent, allowing all fundamental laws to have the same form regardless of the observer's state of motion. The experimental confirmation of these predictions has been overwhelming and continuous since Einstein first proposed them. In particle accelerators, physicists routinely accelerate particles to speeds exceeding 99.9% of light speed. These particles behave exactly as relativity predicts. Their masses increase with velocity, requiring ever more energy to accelerate them further. They decay more slowly than identical particles at rest. their internal clocks running slow due to time dilation. The mathematics of relativity is not optional in designing particle accelerators. It is essential. Without accounting for relativistic effects, the particles would not hit their targets. The collision energies would be miscalculated, and the entire enterprise would fail. GPS satellites provide another spectacular confirmation of light speed constancy and its implications for time dilation. These satellites orbit Earth at approximately 20,000 kilometers altitude, moving at speeds of about 14,000 kilometers per hour relative to Earth's surface. Due to their velocity, special relativity predicts that clocks on the satellites should run slightly slower than clocks on the ground, about 7 microseconds per day slower. However, there is also a general relativistic effect. The satellites are in a weaker gravitational field than clocks on Earth's surface, and general relativity predicts that clocks run faster in weaker gravitational fields. This effect is larger, causing satellite clocks to run about 45 microseconds per day faster than ground clocks. The net effect is that satellite clocks run about 38 microseconds per day faster than identical clocks on the ground. This might seem like a tiny, negligible difference, but GPS depends on extraordinarily precise timing. The system works by having satellites broadcast timing signals, and receivers on the ground calculate their position by measuring the arrival time of signals from multiple satellites. Light travels approximately 30 centimeters in 1 nanosecond, so a timing error of 1 microsecond translates to a position error of 300 meters. If the relativistic effects were not accounted for, GPS would accumulate positioning errors of about 10 kilometers per day, rendering the system completely useless. The fact that GPS works, that it provides meter-level accuracy day after day, year after year, is a continuous experimental verification that relativity is correct. Every time you use a navigation app on your phone, you are relying on the constancy of light speed and the time dilation it produces. Astronomical observations provide confirmation across cosmic distances and timescales. When we observe binary star systems where one star orbits another, the light from the moving star travels to Earth across interstellar space. If light speed varied depending on the motion of the source, we would see bizarre effects. Light emitted when the star is moving toward us would catch up to light emitted when it is moving away from us, scrambling the observed orbital patterns. But we see nothing of the sort. Binary star orbits appear perfectly consistent with light speed being independent of source motion. Similarly, observations of distant supernovae, gamma-ray bursts, and other cosmic events show no evidence that light speed depends on the motion of its source or changes over the vast distances and times involved in cosmic scale light travel. One particularly elegant test involves particles called neutral pions, which decay into pairs of photons. These pions can be produced moving at various speeds in particle accelerators. If light speed depended on the motion of its source, the photons produced by a fast-moving pion decay would travel at a different speed than photons from a stationary pion decay. Careful measurements show no such effect. All the photons travel at the same speed, regardless of how fast the source pion was moving when it decayed. This directly confirms that light speed is independent of source motion, exactly as Einstein's second postulate requires. These experimental confirmations raise an interesting question. Could the speed of light have been different, or could it change over cosmic time? This touches on deep questions about whether the fundamental constants of nature are truly constant, or might vary. The speed of light appears in many physical formulas and is related to other fundamental constants. The fine structure constant, which describes the strength of the electromagnetic interaction, is proportional to the square of the electron charge divided by the product of the speed of light and Planck's constant. If light speed changed over cosmic history, this would show up as variations in the fine structure constant, which we can measure by examining the absorption spectra of light from distant quasars. The light from these quasars was emitted billions of years ago, and the pattern of absorption lines depends on atomic energy levels, which depend on the fine structure constant. Measurements of these distant absorption spectra have been extraordinarily precise, and they show no significant variation in the fine structure constant over billions of years of cosmic history. There are some controversial claims of tiny variations at the parts per million level, but these are disputed and not yet confirmed. The overwhelming evidence is that the fine structure constant, and therefore the speed of light, has remained constant to very high precision throughout the observable history of the universe. This is consistent with theoretical expectations. The speed of light is not a free parameter that could take on different values. It is built into the structure of space-time itself, and changing it would require changing the fundamental geometry of the universe in ways that seem inconsistent with everything we observe. Could the speed of light have been different in a different universe? Or would it necessarily have the value it has? This is a question that pushes against the boundaries of what physics can answer. In some theoretical frameworks, particularly those involving extra dimensions or varying fundamental constants, the speed of light might indeed be different. But in our universe, with its particular space-time geometry and physical laws, the speed of light appears to be fixed. It is not something that was arbitrarily chosen or that could have turned out differently while keeping everything else the same. The speed of light is intertwined with the electromagnetic coupling strength, with the structure of space-time, with the mass scale of fundamental particles in ways that make it difficult to imagine varying it independently. What we can say is that the speed of light serves as the maximum speed for information transfer, and this creates fundamental horizons for causality and observability. Because nothing can travel faster than light, there are regions of the universe that cannot yet have influenced us, and regions we cannot yet have influenced. The observable universe has a finite radius, currently about 46 billion light-years, determined by the maximum distance from which light has had time to reach us since the Big Bang. Beyond this horizon lie regions of space from which no light, no information, no causal influence of any kind has reached us. These regions might as well not exist as far as any direct observation is concerned. We are fundamentally separated from them by the speed of light limit. Similarly, every point in space has a causal past and a causal future, separated by the speed of light. The causal past of an event consists of all events that could have influenced it, all events from which a light signal or slower influence could have reached it. The causal future consists of all events that it could influence. Events outside both the causal past and causal future are space-like separated from the event in question. They are so far away in space and so close in time that not even light could connect them. Such events have no causal relationship, they cannot influence each other, and their time ordering is ambiguous, different observers disagreeing on which happened first. This causal structure has profound implications for how we think about reality. It means the universe is not a single, universal now extending across all space. There is no moment that is the present, everywhere simultaneously, in any observer-independent sense. Different observers have different notions of simultaneity, different definitions of what events are happening now. The present is local, not global. Only events close enough in space and time to be causally connected have an objective temporal ordering. The rest is relative, depending on the observer's state of motion. This fragmentation of the present, this dissolution of a universal now, is perhaps one of the most philosophically challenging implications of light speed constancy. The relationship between light speed constancy and Einstein's most famous equation, E equals mc squared, reveals another deep aspect of how the universe is structured. This equation, expressing the equivalence of energy and mass, emerges directly from the same principles that make light speed invariant. To see the connection, consider what happens when you accelerate an object. In classical physics, kinetic energy equals 1/2 the mass times the velocity squared. This formula works well at low speeds, but it becomes inaccurate as speeds approach light speed. The correct relativistic formula for kinetic energy is more complicated, involving a factor called gamma that depends on the velocity. As velocity approaches light speed, gamma approaches infinity, and so does the kinetic energy, which is why infinite energy would be required to accelerate a massive object to light speed. But something interesting happens when you examine this relativistic energy formula more carefully. At zero velocity, where the kinetic energy should be zero according to classical physics, the relativistic formula gives a non-zero result. An object at rest still has energy, an intrinsic energy associated with its mass. When you work through the mathematics, this rest energy equals the mass times the speed of light squared. E equals mc squared. This equation tells us that mass and energy are not separate, distinct entities. They are different forms of the same underlying thing. Mass is simply highly concentrated energy, and energy has inertia, resistance to acceleration, just like mass. When you add energy to a system, you increase its mass. When you release energy from a system, you decrease its mass. The speed of light squared serves as the conversion factor between mass units and energy units, and it is a huge number, approximately 90 quadrillion in standard SI units. This means a tiny amount of mass corresponds to an enormous amount of energy. 1 kilogram of mass is equivalent to about 90 petajoules of energy, roughly the energy released by a 20 megaton nuclear weapon. This mass-energy equivalence is not just a theoretical curiosity. It powers the sun and all stars through nuclear fusion, where a small fraction of the mass of hydrogen nuclei is converted to energy when they fuse into helium. It powers nuclear reactors through fission, where a small mass difference between parent and daughter nuclei is released as energy. It appears in particle physics whenever particles are created or destroyed. A photon with sufficient energy can spontaneously produce an electron-positron pair, converting pure energy into particles with mass. Or a particle and antiparticle can annihilate, converting their mass entirely into energy. These processes happen continuously in nature and in our laboratories, and they all obey E equals mc squared with perfect precision. The derivation of this equation depends critically on the constancy of light speed. If light speed varied between observers, the relationship between energy and momentum would be different, and the equivalence of energy and mass would not hold in the simple form E equals mc squared. The equation emerges from requiring that the laws of physics, including energy conservation, have the same form in all inertial reference frames when light speed is constant. The speed of light appears in the equation not because the process involves light or electromagnetic radiation, but because light speed is the fundamental constant relating space and time, and therefore relating energy and mass in space-time geometry. There is a deeper unity here that becomes apparent when you think about what energy and momentum really are in space-time terms. In classical physics, energy and momentum are separate conserved quantities. Energy is conserved in time, momentum is conserved in space. But in relativity, Space and time are unified into space-time, and correspondingly, energy and momentum are unified into a single four-dimensional quantity called the energy momentum. 4-vector. Energy is the time component of this 4-vector. Momentum is the space components. Just as space and time are mixed differently for different observers in relative motion, so energy and momentum are mixed differently. What one observer calls pure energy, another observer moving relative to the first will see as a combination of energy and momentum. The invariant magnitude of the energy momentum, 4-vector, the quantity all observers agree on, equals the rest mass times the speed of light. This mathematical structure reveals that the constancy of light speed is intimately connected to the conservation laws that govern physical processes. Energy conservation and momentum conservation are not arbitrary rules imposed on nature. They emerge from the fundamental symmetries of space-time. The fact that the laws of physics do not change as you move through time leads to energy conservation. The fact that they do not change as you move through space leads to momentum conservation. These are examples of Noether's theorem, one of the deepest results in theoretical physics, which connects symmetries to conservation laws. The constancy of light speed, by unifying space and time into spacetime, naturally unifies these conservation laws into the conservation of the energy momentum, 4-vector. When we step back and reflect on all of this, what emerges is a picture of reality quite different from our naive intuitions. The universe is not a three-dimensional stage on which events unfold over universal time. It is a four-dimensional space-time continuum with a rich geometric structure. The speed of light is not merely a speed at which a particular phenomenon happens to propagate. It is a fundamental feature of space-time geometry, the conversion factor that makes space and time aspects of a single unified structure. It sets the maximum speed for causality, the speed at which cause and effect propagate through the cosmos. It determines how energy and mass are related, how time flows at different rates for different observers, how lengths contract, and how simultaneity is relative. All of this follows from one simple, experimentally verified fact. Light travels at the same speed for all observers in inertial reference frames. Everything else, time dilation, length contraction, the relativity of simultaneity, mass-energy equivalence, the impossibility of reaching light speed, the causal structure of space-time, all of it cascades inevitably from this single postulate, combined with the principle that physical laws should be the same in all inertial frames. The constancy of light speed is not an isolated curiosity. It is the keystone of a vast arch of understanding, and removing it would cause the entire structure to collapse. The philosophical implications are profound and unsettling. Our intuitions about time being universal and absolute are wrong. Our sense that spatial distances are objective and observer-independent is wrong. Our feeling that there is a definite present moment everywhere in the universe is wrong. These intuitions served us well in the low-velocity world of everyday experience, where relativistic effects are utterly negligible. But they are approximations, valid only in a limited domain, and they break down when velocities become significant. Fractions of light speed. The true structure of reality is more subtle and more strange than anything our ancestors imagined. Yet this strange structure is also more unified and more elegant. Space and time, which seemed like entirely different kinds of things, are revealed to be aspects of space-time energy and mass, which seemed fundamentally distinct, are shown to be equivalent. The same geometric structure explains why you cannot accelerate to light speed, why moving clocks run slow, why simultaneity is relative, and how GPS satellites must correct their clocks. The theory fits together with a logical inevitability that is characteristic of deep truth. Each piece supports every other piece, and the whole structure stands or falls together. The constancy of light speed also reveals something about the methodology of physics and how we come to understand nature. Einstein did not discover the constancy of light speed by performing new experiments. The Michelson-Morley experiment was already known, and its null result was puzzling. Einstein's genius was to take this result seriously, to accept it as a fundamental principle rather than an anomaly to be explained away, and to work out the consequences with fearless logical consistency. He asked what kind of universe we must live in if light speed is truly constant for all observers. And he followed the mathematics wherever it led, even when it led to conclusions that contradicted centuries of intuition about the nature of time and space. This is a powerful lesson about scientific progress. Sometimes the path forward requires not new observations, but new ways of thinking about existing observations. It requires questioning assumptions so basic that they seem beyond question. Assumptions like the universality of time or the absoluteness of simultaneity. It requires intellectual courage to follow an argument to its logical conclusion, even when that conclusion seems absurd or impossible. And it requires a certain aesthetic sense, a feeling for which theories are deep and beautiful and which are contrived and artificial. Einstein's theory succeeded not just because it explained the Michelson-Morley result, but because it did so with two simple postulates from which everything else followed with mathematical necessity, rather than through ad hoc adjustments to save existing theory. The story of light speed constancy is also a story about how science reveals hidden unities in nature. Before Einstein, space, time, energy, mass, and light seemed like separate, independent entities. After Einstein, we understand that space and time are unified in space-time. Energy and mass are equivalent forms of the same thing, and light speed is the geometric constant determining space-time structure. What appeared to be 5 different things are revealed to be different aspects of a single underlying reality. This pattern of unification has continued throughout physics. The electromagnetic and weak nuclear forces were unified in the electroweak theory. Quantum mechanics and special relativity were unified in quantum field theory. Each unification reveals deeper patterns and reduces the number of independent principles needed to explain nature. The constancy of light speed even hints at further unifications yet to be achieved. General relativity extends special relativity to include gravity, showing that gravity itself is a manifestation of space-time curvature. Quantum mechanics describes the behavior of matter and fields at microscopic scales. These two great theories of 20th century physics are both supremely successful in their domains, but they are not yet unified. A complete theory of quantum gravity would need to describe space-time itself in quantum terms, and it is not yet clear how this should be done. String theory, loop quantum gravity, and other approaches attempt this unification, but none has yet achieved empirical confirmation. One might expect that such a quantum theory of gravity would modify or invalidate the constancy of light speed at extremely small scales or extremely high energies. Perhaps space-time itself has a discrete, granular structure at the Planck scale, roughly 10 to the minus 35 meters, where quantum fluctuations of geometry become important. At such scales, the smooth space-time of relativity might break down, and with it the precise constancy of light speed. But this is speculation. All current evidence supports light speed constancy across the enormous range of scales we can observe, from subatomic particle physics up to cosmological distances. If there are corrections or modifications at extreme scales beyond our current reach, they must be extraordinarily small, not to have been detected already. What makes light speed constancy particularly remarkable is its universality. It applies to electromagnetic radiation of all wavelengths: radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, gamma rays, all travel at exactly the same speed in vacuum. It applies throughout the observable universe, at all distances and all epochs from early times to the present. It applies to all observers regardless of their state of motion. It is built into the fundamental structure of space-time, and cannot be different in one region from what it is in another without violating local laws of physics. This universality makes the speed of light one of the truly fundamental constants of nature, on par with other dimensionless constants like the fine structure constant or the mass ratios of fundamental particles. The fact that we can measure light speed so precisely is itself remarkable and tells us something about the nature of physical constants. Modern measurements define the speed of light to be exactly 299,792,458 meters per second, not as a measured value with uncertainty, but as a defined constant. This is possible because the meter itself is now defined in terms of the light second. 1 meter is defined as the distance light travels in one divided by 299,792,458 of a second. This reverses the historical relationship. Originally, light speed was measured in terms of independently defined units of length and time. But once measurements became precise enough and the constancy of light speed was firmly established, it made sense to define the length unit in terms of light speed and time, since light speed is more fundamental and more constant than any physical artifact that could serve as a length standard. This definitional choice reflects our confidence that light speed is truly constant. If there were any suspicion that light speed might vary, we could not use it to define the meter. The fact that all measurements of phenomena involving light, performed by different methods at different times and places, consistently confirm the same value shows that light speed is indeed invariant. This consistency extends to measurements involving completely different physical processes. The astronomical measurements that first determined light speed, the electromagnetic theory that predicted it from fundamental constants, the Michelson-Morley experiment that showed its constancy, the particle accelerator experiments that confirm relativistic energy-momentum relations, the GPS timing corrections, all tell the same story. Light speed is constant, universal, and fundamental. In teaching and explaining these ideas, there is often an emphasis on the counterintuitive, strange nature of relativity, and this is appropriate. Relativity does contradict our everyday intuitions, but there is also a sense in which relativity is more intuitive than the alternative. Once you internalize the right perspective, the principle of relativity says that physical laws should look the same to all observers. This is deeply intuitive. Why should the laws of nature care what coordinate system you use or how fast you happen to be moving? The constancy of light speed follows from taking this principle seriously and applying it to electromagnetism. Once you accept that light speed must be constant, the rest of special relativity follows with logical necessity. Each prediction, however strange it might seem, is required for logical consistency. The real mystery, if there is one, is not why light speed is constant, but why the universe has the particular structure it does, with space-time geometry and electromagnetic phenomena and the specific relationships between them that we observe. Why is there something rather than nothing? Why does that something have the mathematical structure? it does rather than some other structure? These questions go beyond physics into metaphysics, and they may not have answers that science can provide. Physics describes how the universe behaves and discovers the mathematical patterns that govern its behavior. It can show that certain consequences follow from certain principles, that observations are consistent with theories, that predictions are confirmed or falsified by experiments. But it does not necessarily explain why the fundamental principles are what they are. What physics does provide is an increasingly unified and elegant description of nature. The constancy of light speed unifies space and time. It explains a vast array of phenomena through a small number of principles. It makes precise, testable predictions that have been confirmed countless times. It reveals hidden connections between seemingly disparate concepts. And it does all this with a mathematical beauty and logical coherence that suggests we are seeing something fundamental about reality, not just an effective description that happens to work in a limited domain. The story of how we came to understand light speed constancy is also inspiring in a human sense. It involved centuries of careful observation and measurement, brilliant theoretical insights, meticulous experiments, heated debates and controversies, flashes of individual genius like Einstein's, and the collective work of the scientific community testing and refining ideas. It showed how human beings, starting from our limited everyday experience in a small corner of the universe, moving at speeds far below light speed, could nonetheless figure out the true structure of space-time. We used mathematics as a language to express physical principles, experiments to test hypotheses, and logical reasoning to work out consequences. And we arrived at a theory that makes successful predictions far beyond the domain in which it was developed. A theory that continues to be confirmed in particle accelerators and GPS satellites and astrophysical observations. This success suggests that human reason, despite its limitations and biases, is capable of understanding fundamental truths about nature. We are not forever trapped by the parochial perspective of our particular evolutionary history and everyday experience. We can use mathematics and logic and experiment to extend our understanding far beyond what our unaided senses could ever reveal. The constancy of light speed, hidden from casual observation because everyday speeds are so much slower than light, was nonetheless discovered and understood through careful thought and measurement. This is a testament to the power of the scientific method and the human capacity for abstract reasoning. Looking forward, the constancy of light speed will continue to be central to physics as we probe deeper into nature. Any theory that goes beyond general relativity and quantum field theory, any theory of quantum gravity or grand unification, will have to respect light speed constancy as an experimental fact across all currently accessible scales. It is possible that at scales or energies far beyond what we can currently probe, new physics might modify or extend relativity in ways we do not yet understand. But any such modification will have to reproduce light speed constancy as an extremely accurate approximation in the domain where we have tested it. The constancy of light speed also has practical implications for the future. As space travel advances, if we ever develop technologies to send spacecraft at significant fractions of light speed, relativistic effects will become directly relevant to mission planning. Time. Dilation will mean that travelers age differently from people who remain on Earth. Length contraction will affect the geometry of fast-moving objects. The finite speed of light will impose fundamental limits on how quickly we can communicate across interstellar distances. These are not distant theoretical concerns. They are practical constraints that any advanced civilization must deal with. Similarly, as technology continues to advance, we are building devices that operate at higher energies, faster speeds, and greater precisions, where relativistic effects become more important. Particle accelerators already operate in the fully relativistic regime. Future quantum computers and quantum communication networks may need to account for relativistic effects on quantum entanglement and information transmission. High-precision atomic clocks for navigation and fundamental research must account for time dilation. The constancy of light speed is not just a fascinating theoretical principle. It is a practical fact that engineers and technologists must incorporate into their designs. In fundamental research, tests of light speed constancy continue to improve in precision. Physicists measure whether light speed varies with photon energy, with direction, with location, with time. They look for the tiniest deviations from perfect constancy that might hint at new physics. So far, all such tests have confirmed constancy to extraordinary precision, but the search continues because any confirmed violation would be a revolutionary discovery, suggesting new phenomena beyond current theories. The constancy of light speed is so fundamental that any deviation from it would require rebuilding large parts of physics. There is something deeply satisfying about how light speed constancy unifies so many aspects of physics into a coherent whole. The same principle explains why you cannot send signals faster than light, why moving clocks run slow, why GPS satellites need time corrections, why particle accelerators work the way they do, why nuclear weapons release so much energy, and why the universe has a cosmic speed limit. This explanatory power, this ability to account for diverse phenomena through a single principle, is a hallmark of successful scientific theory. It suggests we have identified something fundamental rather than merely described superficial patterns. The constancy of light speed also connects to deep questions about the nature of physical law. Why do laws of physics have mathematical form? Why are they the same everywhere and every when? Why do they apply universally rather than varying from place to place? The constancy of light speed follows from the universality of physical law. If Maxwell's equations are valid laws of physics, they must have the same form in all inertial frames, which requires light speed to be constant. This connection between mathematical form, universality, and constancy reveals something about the deep structure of natural law. Though it is not yet clear whether this is something we can explain or must simply accept as given. From a philosophical perspective, the constancy of light speed challenges our naive realism about space and time. We naturally think of space and time as absolute background frameworks in which events occur. We imagine that there is a fact of the matter about how much space separates two objects and how much time elapses between two events, independent of any observer. Relativity shows this is wrong. Spatial and temporal separations are observer-dependent. What is objective is the space-time interval combining space and time. And this is where light speed enters as the conversion factor. The objective reality is four-dimensional space-time, not three-dimensional space plus time. This raises questions about the nature of existence and reality. If time is relative, if there is no universal present, what does it mean to say something exists now? Does the past still exist in some sense, and the future already exist, with all of time laid out as a single four-dimensional block? Or does only the present exist, even though different observers disagree about what the present is? These questions touch on metaphysics and philosophy of time, areas where physics constrains but does not fully determine the answers. The constancy of light speed and the relativity it implies force us to think carefully about these questions, even if definitive answers remain elusive. Another philosophical dimension concerns scientific realism versus instrumentalism. Should we believe that space-time really exists as a four-dimensional continuum? Or is this just a useful mathematical tool for organizing observations? Should we believe that time really dilates and lengths really contract? Or are these just artifacts of how we measure things? Most physicists are realists in practice. They talk and think as if space-time is real, not just a convenient fiction. This is partly because relativity is so successful and makes such precise predictions that it seems unreasonable to deny it represents genuine knowledge about reality. But it is also because the alternative, treating it as mere instrumentalism, makes it hard to explain why the theory works so well. The constancy of light speed illustrates how scientific progress can require conceptual revolutions, not just accumulation of facts. Before Einstein, physicists were gathering more and more data, refining measurements, proposing modifications to existing theories. But no amount of data gathering within the old conceptual framework could have led to relativity. What was needed was a new way of thinking, a willingness to question basic assumptions, and the courage to follow logical arguments even when they led to bizarre conclusions. Einstein provided this conceptual revolution, and physics was transformed. Similar revolutions happened with quantum mechanics, and they may happen again as we develop theories of quantum gravity or discover new phenomena beyond the standard model. Teaching relativity and explaining light speed constancy faces the challenge of overcoming deeply ingrained intuitions. Students naturally think in terms of absolute time and space because this approximation works perfectly well in everyday life. Convincing them that reality is different at high speeds requires both careful logical argument and exposure to experimental evidence. The historical approach, showing how the puzzle of light speed emerged and how Einstein solved it, helps make the conceptual revolution more understandable. So does emphasizing the internal logical consistency of relativity, how each strange prediction follows necessarily from the basic postulates. The mathematics of relativity is not particularly difficult compared to other areas of physics. The key equations can be derived with algebra and basic calculus. What makes relativity challenging is not the math, but the concepts. Understanding what time dilation really means, visualizing space-time diagrams, thinking in terms of four-dimensional geometry rather than three-dimensional space evolving over time. These conceptual shifts require effort and practice, but once achieved, they provide a much deeper understanding of nature and reveal the universe to be more subtle and more interesting than naive intuition suggests. The experimental tests of light speed constancy and relativistic predictions provide compelling evidence that the theory is correct, not just mathematically consistent. When GPS works, when particle accelerators successfully collide particles at predicted energies, when astronomical observations match relativistic calculations, when atomic clocks show predicted time dilation, all of this confirms that we are not just playing mathematical games, but describing real features of the physical universe. The theory makes precise, quantitative predictions that could easily be falsified if they were wrong. Yet experiment after experiment confirms them. This empirical success is what distinguishes relativity from mere speculation or philosophy. Anyone can propose an alternative theory with different assumptions, and people do. But unless that alternative theory makes predictions that agree with experiment as precisely as relativity does, it cannot replace relativity, and so far, no alternative has succeeded. Various modifications and extensions have been proposed, theories with varying speed of light, theories with preferred reference frames, theories with different space-time geometries. Some of these are still viable as extensions beyond known physics at extreme scales. But in the regime we can test, relativity, with its constant light speed, reigns supreme. The constancy of light speed also connects to questions about the limits of knowledge. There are regions of space-time from which no signal can ever reach us, because they are beyond our cosmic horizon. There are aspects of black hole interiors hidden behind event horizons. There may be features of quantum gravity at Planck scales that we can never directly observe. These limitations are not technological but fundamental, rooted in the finite speed of light and the structure of space-time. This suggests that complete knowledge of the entire universe may be impossible in principle, not just in practice. We are fundamentally limited by causal horizons determined by light speed. Yet, within these limitations, our knowledge can be remarkably deep. We understand the structure of space-time, the unification of space and time, the equivalence of energy and mass, the causal structure of events. We can make precise predictions about phenomena we have never directly observed: the behavior of matter near black holes, the gravitational waves from merging neutron stars, the time dilation experienced by cosmic ray muons. And these predictions are confirmed when we do finally observe these phenomena. This suggests that our theories capture genuine truths about nature, not just convenient approximations. The story of light speed constancy is ultimately a story about the power of human reason to uncover deep truths about reality. Starting from puzzling experimental results and theoretical inconsistencies, Einstein and others developed a theory that revolutionized our understanding of space, time, matter, and energy. This theory made bizarre, counterintuitive predictions that have been confirmed countless times across vast ranges of scale and circumstance. It unified previously separate concepts and revealed unexpected connections. And it did all this through a combination of logical reasoning, mathematical analysis, and empirical testing, the essential methods of science. As we conclude this exploration, we return to the simple fact with which we began. Light travels at exactly 299,792,458 meters per second in vacuum, and this speed is constant for all observers regardless of their motion. This one simple fact, properly understood, requires us to reconceive space, time, causality, and the very fabric of reality itself. Space and time are not absolute and universal. They are relative and observer-dependent. Time flows at different rates for different observers, lengths contract, simultaneity is relative, and mass and energy are equivalent. The universe has a fundamental speed limit, a maximum rate at which cause and effect can propagate. Space-time is a unified four-dimensional continuum with a rich geometric structure, and light speed is the conversion factor that relates its spatial and temporal aspects. All of this follows from light speed constancy combined with the principle that physical laws should be the same in all inertial frames. These two simple postulates give rise to the entire theory of special relativity with all its strange and profound consequences. The theory has been tested exhaustively for over a century and has passed every test. It is built into our most advanced technologies and our deepest theories of matter and force. It shapes how we understand the cosmos, from subatomic particles to the entire observable universe. And it all comes down to this: light speed is constant. This single fact is a window into the fundamental structure of reality, revealing that the universe is far more subtle, more elegant, and more deeply interconnected than our everyday experience could ever suggest. The constancy of light speed stands as one of the great discoveries of human civilization. comparable to the realization that Earth orbits the Sun or that matter is made of atoms. It required centuries of scientific progress to recognize, a conceptual revolution to understand, and it continues to shape our exploration of nature. As we push our understanding further, probing quantum gravity, searching for new physics beyond the standard model, exploring the cosmos with ever more powerful instruments, the constancy of light speed remains a guiding principle, a tested truth, a fundamental feature of the universe we inhabit. It reminds us that reality is often stranger than fiction, that mathematics is a powerful tool for understanding nature, and that human reason, carefully applied, can penetrate deeply into the mysteries of existence. The profound implications of light speed constancy extend into every corner of physics and ripple outward into technology, philosophy, and our understanding of existence itself. To truly appreciate the depth of this principle, we must examine more carefully how it manifests in specific physical situations and what it tells us about the architecture of reality. The constancy of light speed is not merely an isolated fact to be memorized. It is a thread that, when pulled, unravels our entire intuitive picture of the universe and forces us to weave a new one from fundamentally different conceptual materials. Consider the twin paradox, one of the most famous thought experiments in relativity. Imagine identical twins, one who remains on Earth and another who boards a spaceship and travels to a distant star at very high speed before returning. According to time dilation, the traveling twin's clock runs slow relative to Earth's reference frame, so the traveling twin should age less during the journey. When the twins reunite, the traveler should be younger than the stay-at-home twin. But here's the apparent paradox. From the traveler's perspective, Earth is moving away at high speed, so shouldn't Earth's clocks be running slow? Shouldn't the earthbound twin be the younger one? Both perspectives seem symmetric, yet they cannot both be right. When the twins meet, either one is younger or they are the same age. There cannot be two different outcomes. The resolution of this paradox lies in recognizing that the situation is not actually symmetric. The traveling twin must accelerate to reach high speed, decelerate to turn around at the distant star, and accelerate again to return home. The earthbound twin remains in an inertial reference frame throughout the journey, but the traveling twin does not. The periods of acceleration break the symmetry of the situation. During acceleration, the traveling twin is not in an inertial frame, and the special relativity analysis, based on constant velocity motion, does not directly apply. When you properly account for the acceleration phases using general relativity, or even by carefully analyzing the situation from multiple inertial frames in special relativity, the asymmetry becomes clear. The traveling twin genuinely ages less, and both twins agree on this result when they reunite. This is not just a theoretical curiosity. The effect has been measured directly using atomic clocks flown around the world in airplanes. In 1971, Joseph Haffel and Richard Keating flew atomic clocks on commercial flights, some traveling eastward around the world and others westward. When they compared these clocks to reference clocks that remained on the ground, they found exactly the time differences predicted by relativity. The eastward flying clocks lost time compared to the ground clocks, while the westward flying clocks gained time, with the differences arising from a combination of special relativistic effects due to the plane's velocities and general relativistic effects due to their altitude. The measurements matched the predictions to within experimental uncertainty, providing direct confirmation that moving clocks genuinely do run at different rates. More dramatically, cosmic ray muons provide a natural demonstration of time dilation on a massive scale. Muons are unstable particles that decay with a half-life of about 2.2 microseconds. When at rest, they are created high in Earth's atmosphere, about 15 kilometers up, when cosmic rays collide with atmospheric atoms. Even traveling at nearly the speed of light, a muon should only travel about 660 meters before half of them decay, far short of the distance needed to reach the ground. Yet, we detect large numbers of muons at sea level. How is this possible? The answer is time dilation. From the muon's perspective, they are at rest and their clocks tick normally, but the distance to Earth's surface is length contracted due to their high speed relative to Earth. From Earth's perspective, the muons are moving at nearly light speed, and their internal clocks run slow due to time dilation. So they live much longer as measured by Earth clocks, allowing them to reach the surface before decaying. Both perspectives give the same physical result. Muons reach the ground, but they explain it differently due to their different reference frames. This is relativity in action, observed constantly in the natural particle flux. Hitting Earth. The length contraction aspect deserves more detailed examination because it reveals something subtle about the nature of space in relativity. When we say a moving object contracts in the direction of motion, we must be careful about what this means. The contraction is not a physical compression in the sense of squeezing atoms closer together through mechanical forces. Rather, it is a geometric effect of how space and time are measured in different reference frames. An object has a proper length, the length measured in its rest frame, where all points on the object are measured simultaneously according to that frame's notion of simultaneity. When a different observer measures the same object's length, they must mark the positions of both ends simultaneously according to their notion of simultaneity. But because of the relativity of simultaneity, what is simultaneous in the moving frame is not simultaneous in the stationary frame, and this difference leads to different length measurements. To make this concrete, imagine a long train moving at high speed past a station platform. The train has a proper length of 1 kilometer as measured by passengers on the train. An observer on the platform wants to measure the train's length and does so by noting the positions of the front and back of the train at the same moment according to platform time. Due to length contraction, the observer measures something less than 1 kilometer, perhaps 866 meters, if the train is moving at half the speed of light. Now consider the perspective from the train. Passengers on the train see the platform moving backward at high speed. So from their perspective, the platform is length contracted. If there are markers on the platform spaced 1 kilometer apart in the platform's rest frame, passengers on the train will measure these markers as being closer together than 1 kilometer. This reciprocal nature of length contraction seems paradoxical at first, but it is not. The key is that different observers are measuring different things. The platform observer measures the train's length by marking where both ends are at the same platform time. The train passengers measure the distance between platform markers by noting their positions at the same train time. These are different measurements, performed at different sets of events in space-time, and it is perfectly consistent for both to show contraction. When you draw space-time diagrams showing the world lines of all relevant objects and events, everything fits together consistently with no contradictions. The relativity of simultaneity is crucial to understanding these apparent paradoxes. Yet, it is perhaps the most counterintuitive aspect of relativity. Our brains are wired to think of the present as a universal now, a moment that extends across all space simultaneously. We imagine that when we say, right now, Mars is in a particular position in its orbit, there is an objective fact about where Mars is at this very instant. But relativity says this is wrong. There is no observer-independent fact about what is happening on Mars right now. Different observers in different states of motion will disagree about which events on Mars are simultaneous with a given event on Earth. These disagreements are not due to signal delays or limitations of observation. They are fundamental features of space-time geometry. To see why simultaneity must be relative if light speed is constant, imagine two observers, Alice and Bob, with Bob moving at high speed relative to Alice. Alice has two light sources equidistant from her, one in front and one behind. She turns them on simultaneously, according to her, and the light from both sources reaches her at the same time, confirming they were simultaneous in her frame. But from Bob's perspective, he is at rest and Alice is moving. When Alice turns on the light sources, Bob sees that Alice is moving toward the light from the front source and away from the light from the rear source. Since light speed is constant in Bob's frame, and the light from both sources reaches Alice simultaneously, even though she is moving toward one and away from the other, Bob must conclude that the rear light was turned on earlier than the front light. Events that are simultaneous in Alice's frame are not simultaneous in Bob's frame. This relativity of simultaneity means that the very concept of the present is local, not global. You can meaningfully talk about what is present at your location right now, but you cannot extend this to a universal present throughout the universe. The set of events that you consider simultaneous with your present moment is different from the set that a moving observer considers simultaneous with their present moment. This doesn't mean that everything is subjective or arbitrary. All observers agree on which events are causally connected, on the invariant space-time interval between events, on the outcomes of physical processes. But they slice space-time into space and time differently, leading to different judgments about simultaneity, duration, and spatial distance. This fundamentally changes how we must think about reality. In the classical picture, the universe exists as a three-dimensional space that evolves over time, with a definite state at each moment. The past is gone, the future has not yet happened, and only the present exists. But if different observers disagree about what is present, this picture becomes incoherent. How can only the present exist if observers disagree about what the present is? This has led many physicists and philosophers to adopt the block universe view, in which all of space-time exists equally, with past, present, and future all laid out as a single four-dimensional structure. The flow of time is then understood as the progression of consciousness through this structure, or perhaps as an emergent feature of how we perceive thermodynamic processes, but not as an objective feature of the universe itself. Not everyone accepts this block universe interpretation. Some argue for a more nuanced view where the past is fixed, the future is open, but the present is relative to observer perspective. Others try to maintain some version of presentism compatible with relativity. These debates touch on deep questions in the philosophy of time and the nature of existence that physics constrains but does not fully resolve. What physics tells us unambiguously is that simultaneity is relative, that there is no universal present, and that space-time has a four-dimensional structure. How we interpret these facts metaphysically remains somewhat open. The constancy of light speed also has profound implications for our understanding of causality that go beyond the simple statement that nothing can travel faster than light. It determines the causal structure of space-time in a precise mathematical way. For any event in space-time, we can divide all other events into three categories based on their relationship to that event. First, the past light cone consists of all events from which a light signal could have reached the given event. These are events that could have causally influenced the given event. Second, the future light cone consists of all events that a light signal from the given event could reach. These are events that the given event could causally influence. Third, elsewhere consists of all events that are space-like, separated from the given event. Too far away in space and too close in time for light to connect them. Events in elsewhere cannot causally influence the given event, nor can the given event influence them. This structure is observer-independent. All observers agree on whether two events are causally connected, even though they may disagree on the spatial distance or time separation between them. The speed of light serves as the boundary between time-like separated events, which can be causally connected, and space-like separated events, which cannot. This is why light speed is often called the speed of causality. It is the maximum speed at which information, energy, or any physical influence can propagate. Anything that travels faster than light would connect space-like separated events, potentially allowing causal loops and violations of causality that seem logically impossible. There have been various proposals and speculations about faster-than-light phenomena: tachyons, wormholes, warp drives, quantum entanglement as superluminal communication. Each of these must be examined carefully to see whether it genuinely allows faster-than-light information transfer. Tachyons, hypothetical particles that always travel faster than light, have never been observed and create numerous theoretical problems, including potential violations of causality. Most physicists suspect they do not exist. Wormholes and warp drives are solutions to Einstein's equations of general relativity that might allow effective faster-than-light travel through space-time manipulation, but they require exotic matter with negative energy density that may not exist, and they may still not allow violation of causality when analyzed carefully. Quantum entanglement allows correlations between distant measurements to exceed what classical physics allows, but it cannot be used to send information faster than light, because the correlations only become apparent when you compare measurements through classical, slower-than-light communication channels. The distinction between correlation and causation is crucial here. Quantum entanglement creates correlations. Measurements on entangled particles show stronger statistical relationships than classical physics permits. But correlation is not causation, and correlation alone cannot send information. If you measure one particle of an entangled pair and get a random result, and I measure the other particle and also get a random result, the fact that our random results are correlated does not let you send me a message. You have no control over which result you get, so you cannot encode information in your measurement outcome. Only when we later compare our results through classical communication do we see the correlation. This classical comparison step must be slower than light, so quantum entanglement does not provide faster than light communication, even though it creates stronger than classical correlations. This is fortunate because faster than light communication would create severe logical problems. If you could send a message instantaneously from your frame, someone moving at high speed relative to you would see the message arrive before it was sent, due to the relativity of simultaneity. They could then send an instantaneous reply, which would arrive back at you before you sent the original message from your perspective. This allows closed causal loops where effects precede causes, leading to logical paradoxes. The fact that nature prevents faster-than-light information transfer preserves the logical consistency of causality across different reference frames. The speed of light also determines how we observe the universe astronomically. When we look at distant objects, we see them not as they are now, but as they were when the light we receive was emitted. The light from the sun takes about 8 minutes to reach Earth, so we see the sun as it was 8 minutes ago. The nearest star beyond the sun, Proxima Centauri, is about 4 light-years away, so we see it as it was 4 years ago. Distant galaxies are millions or billions of light years away, so we see them as they were in the distant past. The most distant objects we can observe, the cosmic microwave background radiation, shows us the universe as it was about 13.8 billion years ago, just 380,000 years after the Big Bang, when the universe first became transparent to light. This means that astronomy is inherently a study of history. We cannot see the current state of distant objects. We can only see their past. The farther away something is, the farther into the past we observe. This creates a remarkable situation where we can observe the history of the universe directly by looking at objects at different distances. Nearby galaxies show us what galaxies look like relatively recently. More distant galaxies show us what they looked like billions of years ago when the universe was younger. The most distant galaxies we can observe are seen as they were when the universe was less than 1 billion years old, shortly after the first stars and galaxies formed. By observing objects at different distances, we can trace cosmic evolution over billions of years. This historical aspect of observation also means that some events we observe now happened so long ago that the objects involved no longer exist or have changed completely. A supernova we observe in a galaxy 100 million light years away actually exploded 100 million years ago. The star is long gone, but its light is just now reaching us. Similarly, there are events happening right now throughout the universe that we cannot yet observe, because their light has not had time to reach us. The finite speed of light creates a fundamental limitation on our knowledge of the current state of the universe. We are surrounded by a horizon determined by how far light could have traveled since the Big Bang. And we cannot see beyond this horizon, not because our telescopes are inadequate, but because the light simply has not had time to reach us yet. Interestingly, this cosmic horizon is not fixed. It expands as the universe ages, and light from more distant regions has time to reach us. However, due to the accelerating expansion of the universe driven by dark energy, there are regions currently visible that will eventually disappear beyond our horizon. The acceleration means that light from very distant galaxies is being redshifted to longer and longer wavelengths as space expands. And eventually, these galaxies will recede so fast that their light can never catch up to us. They will fade from view, not because they cease to exist, but because the expansion of space carries them away from us faster than light can cross the ever-increasing distance. This is not a violation of light speed constancy. The galaxies are not moving through space faster than light, but rather space itself is expanding, carrying distant galaxies away from us. This expansion of space raises interesting questions about light speed and cosmology. The speed of light is constant locally. If you measure light passing by you, you always get the same answer regardless of your motion. But when light travels across cosmological distances, space itself expands during the light's journey, affecting the light's wavelength and the relationship between distance and travel time. Photons from the cosmic microwave background have traveled for 13.8 billion years, but the region they came from is now about 46 billion light-years away due to expansion. This does not contradict light speed constancy. The photons traveled at light speed through space the whole time, but space itself stretched during their journey, increasing the current distance to their point of origin. Understanding how light propagates through expanding space requires general relativity, which extends special relativity to include gravity and dynamic spacetime geometry. In general relativity, the constancy of light speed is a local principle. Light always travels at c through the local spacetime geometry as measured by local observers using local clocks and rulers. But global properties like the total distance, light travels, or the relationship between emission and observation wavelengths depend on how spacetime curves and expands between emission and observation. This adds richness and complexity to cosmology while preserving the fundamental principle that light speed is locally constant. The mathematical structure underlying all of this is elegant and surprisingly simple once you understand the right framework. Special relativity can be formulated using Minkowski spacetime, named after Hermann Minkowski, who developed the geometric formulation shortly after Einstein's 1905 paper. In Minkowski spacetime, events are points specified by 4 coordinates, 3 spatial coordinates and 1 time coordinate multiplied by the speed of light to give it units of length. The interval between 2 events is calculated using a formula similar to the Pythagorean theorem, but with a crucial difference. The time term enters with opposite sign from the spatial terms. This difference in sign, more than anything else, encodes the distinction between space and time and the special role of light speed. The invariant spacetime interval between 2 events is delta s squared equals c squared. Delta t squared minus delta x squared minus delta y squared minus delta z squared, where delta t is the time difference and delta x, delta y, delta z are the spatial coordinate differences. This quantity is the same for all inertial observers, even though they disagree about the individual values of delta t, delta x, delta y, and delta zt. When delta s squared is positive, the events are timelike, separated, and could be causally connected. When delta s squared is negative, making the interval imaginary, or we can define a spacelike interval with the opposite sign. The events are spacelike separated and cannot be causally connected. When delta s squared equals 0, the events are light-like separated. They could be connected by a light signal traveling at exactly light speed. This geometric formulation makes many aspects of relativity clearer. Time dilation and length contraction emerge naturally from the requirement that the spacetime interval be invariant. The velocity addition formula, which shows how velocities combine in relativity, and which gives a different result than simple classical addition, follows from the geometry. The relationship between energy and momentum, including the rest energy, equals mc squared, comes from the 4-dimensional energy-momentum vector and its invariant magnitude. All the seemingly disparate phenomena of special relativity are unified as geometric features of Minkowski spacetime. One particularly illuminating way to visualize this is through spacetime diagrams, where time is plotted vertically and one spatial dimension horizontally. An object at rest traces a vertical line, moving through time but not space. A moving object traces a tilted line, with the tilt representing its velocity light. Moving at c traces lines at a 45-degree angle if we choose units where c equals 1. These 45-degree light paths define light cones from every point, separating time-like from space-like regions. Events connected by lines steeper than 45 degrees are time-like separated. Events connected by lines shallower than 45 degrees are space-like separated. And events connected by exactly 45-degree lines are light-like separated. Different inertial observers have different notions of which direction is time and which is space in these diagrams. They effectively rotate the time and space axes in opposite directions, but always keeping the light cones fixed at 45 degrees. This is the geometric content of the Lorentz transformation that relates measurements in different frames. The invariance of light speed corresponds to the fact that light cone angles are the same for all observers. The relativity of simultaneity corresponds to different observers having different horizontal, simultaneous directions in the diagram. Time dilation and length contraction correspond to how intervals along the time and space axes transform when you rotate to a different frame. These geometric insights extend to four-dimensional rotations when you include all three spatial dimensions. A Lorentz transformation, which converts between different inertial frames, is a kind of rotation in four-dimensional spacetime, but with a crucial difference from ordinary rotations. It preserves the spacetime interval delta s squared rather than the Euclidean distance, and this leads to the hyperbolic geometry of Minkowski space, rather than the spherical geometry of Euclidean rotations. The mathematical group describing these transformations is called the Lorentz group, and it has been studied extensively by physicists and mathematicians. Its structure underlies not just special relativity, but also quantum field theory and the standard model of particle physics. The connection between light speed constancy and symmetry principles goes even deeper when you examine quantum field theory. In quantum field theory, particles are understood as excitations of underlying quantum fields that pervade spacetime. These fields must transform properly under Lorentz transformations to preserve the invariance of light speed and the principle of relativity. This requirement severely constrains the possible forms that quantum field theories can take. The masses of particles, the strengths of their interactions, the types of fields that can exist. All of these are constrained by Lorentz invariance, the requirement that physics looks the same in all inertial frames. For example, the photon must be massless in order for electromagnetism to be consistent with Lorentz invariance. A massive photon would travel slower than light speed, and Maxwell's equations would need to be modified in ways that violate the principle of relativity. Similarly, gravitons, the hypothetical quantum particles of gravity, must be massless because they must travel at light speed to mediate gravitational effects consistently across different reference frames. The masses of other particles like electrons and quarks are parameters in the theory, but the way mass appears in the equations is fixed by Lorentz invariance. The entire structure of the Standard Model, our most successful theory of particle physics, is built on the foundation of Lorentz invariance and the constancy of light speed. This connection between symmetry and physical law is one of the deepest insights of 20th century physics. Emmy Noether proved her famous theorem showing that every continuous symmetry of a physical system corresponds to a conservation law. Time translation symmetry, the laws don't change over time, leads to Ishi, energy conservation. Space translation symmetry, the laws don't change from place to place, leads to momentum conservation. Rotational symmetry leads to angular momentum conservation. Lorentz invariance, the symmetry underlying special relativity and light speed constancy, is even more fundamental. It constrains the very form that physical laws can take. This is why violations of light speed, constancy, or Lorentz invariance are taken so seriously by physicists. Any confirmed violation would not just require adjusting one parameter in our theories. It would force a fundamental rethinking of how we formulate physical laws. For this reason, there are ongoing experimental programs to test Lorentz invariance with ever-increasing precision, looking for the tiniest deviations that might hint at new physics. So far, these tests have found nothing. Lorentz invariance holds to extraordinary precision across all accessible scales and in all types of interactions. The connection between light speed and the electromagnetic force also deserves deeper examination. In quantum electrodynamics, QED, the quantum field theory of electromagnetism, photons are the force carriers that mediate electromagnetic interactions between charged particles. When two electrons repel each other electromagnetically, this is understood in QED as occurring through the exchange of virtual photons. Photons that exist briefly, carrying energy and momentum between the electrons, but not lasting long enough to be directly observed. These virtual photons travel at light speed, and this is why electromagnetic effects propagate at light speed. If you wiggle an electron here, the electromagnetic disturbance travels outward at light speed, carried by real photons in the classical limit, or by the quantum field in the full quantum treatment. An electron over there responds to this disturbance only after enough time has passed for light to cross the distance. This is not instantaneous action at a distance. It is local interaction mediated by fields propagating at finite speed. The finite light speed ensures that electromagnetic causality is preserved, that causes precede effects, and that no paradoxes arise from attempting to signal faster than light using electromagnetic phenomena. The unification of electricity and magnetism that Maxwell achieved in the 19th century turns out to be deeply connected to relativity. What one observer sees as a purely electric field, another observer in relative motion may see as a combination of electric and magnetic fields. The separation of electromagnetic phenomena into electric and magnetic is frame-dependent, just as the separation of space-time into space and time is frame-dependent. The truly fundamental object is the electromagnetic field. Tensor, a mathematical entity that combines electric and magnetic fields into a unified whole and transforms properly under Lorentz transformations. This unification of electricity and magnetism is not separate from the unification of space and time. They are intimately connected aspects of the same underlying structure. Similarly, what we call energy and what we call momentum are not truly separate. They are components of the energy-momentum 4-vector, unified in the same way that space and time are unified. An object's rest energy, its kinetic energy, and its momentum are all aspects of this 4-vector, and different observers mix them differently depending on their relative motion. The famous equation E equals mc squared is actually just one component of a more general relationship involving the full energy-momentum 4-vector. The complete equation is E squared equals pc squared plus mc squared, where E is total energy, P is momentum magnitude, m is rest mass, and c is light speed. For an object at rest, P equals 0, this reduces to E equals mc squared. For a photon, m equals 0, this gives E equals pc, relating photon energy to momentum through light speed. This brings us back to the question of why massless particles must travel at light speed. The answer lies in the structure of the energy-momentum relation. For a massless particle, E equals pc. The ratio of energy to momentum is c, the speed of light. But energy divided by momentum is also equal to velocity for any classical object. The quantum relation between energy and momentum for a photon, E equals pc, combined with the classical relationship between energy, momentum, and velocity, forces photons to travel at velocity ce. They cannot travel slower because that would be inconsistent with having zero mass. They cannot travel faster because, well, nothing can travel faster because it would require either imaginary mass or imaginary energy, neither of which makes physical sense. The mathematics prevents faster-than-light travel, not through some arbitrary rule, but through the fundamental structure of how energy, momentum, mass, and velocity are related in spacetime. These relationships are not optional. They follow from the requirement that physics be consistent with the geometry of spacetime and the invariance of light speed. You cannot tinker with one part without breaking the entire framework. This is what gives relativity its logical inevitability. Once you accept the basic postulates, everything else follows with iron logic. Understanding light speed constancy also illuminates various apparent paradoxes and puzzles that have confused students and sometimes even professional physicists. The ladder paradox is one famous example. Imagine a ladder moving at very high speed horizontally toward an open garage. The ladder's proper length is longer than the garage, but due to length contraction, an observer at rest relative to the garage sees the moving ladder contracted and shorter than the garage. At some instant in the garage frame, the entire ladder is inside the garage, and doors could close at both ends, trapping the ladder inside. But from the ladder's perspective, the ladder is at its proper length, and the garage is moving toward it and length. Contracted, so the ladder is longer than the garage. How can the ladder both fit and not fit inside the garage? The resolution is the relativity of simultaneity. The garage observer says both doors close simultaneously when the ladder is entirely inside. But in the ladder's frame, these two door-closing events are not simultaneous. The rear door closes first, then the front door closes later, after the ladder has moved forward. At no instant in the ladder frame is the ladder entirely enclosed with both doors closed. Both descriptions are correct in their respective frames, and there is no contradiction when you carefully track which events are simultaneous in which frame. The physical outcome, whether anything breaks, what marks are left, what observers actually see, is agreed upon by all observers. Only the description of what happens simultaneously differs. Another instructive puzzle involves spaceships and strings. Imagine two identical spaceships initially at rest and separated by some distance with a string connecting them. They simultaneously, in their initial rest frame, fire their engines and accelerate identically toward the same final velocity. What happens to the string? You might think it remains unstretched since both ships accelerate identically. But the correct answer is that the string breaks. The reason is that length contraction is a real physical effect, not just a measurement artifact. As the ships accelerate, the distance between them as measured in the original rest frame remains constant by construction. But in the final moving frame, length contracted distances appear longer in the original frame. So to maintain constant separation in the original frame, the proper distance between the ships, their separation in their own frame, must increase. The string cannot stretch to accommodate this increase, so it breaks. This seems strange, but it follows directly from the geometry of spacetime and the relativity of simultaneity. Events that are simultaneous in the original rest frame, the two ships firing their engines at the same moment, are not simultaneous in the accelerating frame. In the moving frame, one ship fires before the other, so they end up farther apart than they started. The breaking of the string is a real physical event that all observers agree on, even though they describe it differently. The garage observer says the string breaks because the ships maintain constant separation in the garage frame, which corresponds to increasing proper separation. The ship's final frame says the string breaks because the ships fired at different times and therefore ended up farther apart than they started. Different descriptions, same physical outcome. These apparent paradoxes all have the same resolution. carefully track events in spacetime, properly account for the relativity of simultaneity, and remember that what is being measured differs between frames. There are no actual contradictions, just the need to think carefully about relativistic geometry rather than applying classical intuitions. The constancy of light speed enforces this strange geometry, and all its consequences, however counterintuitive, follow inexorably. The implications extend beyond physics into questions about consciousness, free will, and the nature of time. If the block universe view is correct, and all of space-time exists as a single four-dimensional whole, does this mean the future is already determined? If events that are in our future already exist in some objective sense, located at future time coordinates in the space-time manifold, how can we have free will to affect them? These are deep philosophical questions without clear answers. One response is that determinism versus free will is not primarily a question about the structure of space-time, but about the nature of physical law. If physical laws are deterministic, which quantum mechanics suggests they are not at a fundamental level, then the state of the universe at one time determines its state at all future times, regardless of whether we view time as flowing or as a dimension of a static spacetime. If physical laws are indeterministic, allowing genuine randomness or free will, then the future is not determined even if it exists, in some sense, as part of spacetime. The block universe view tells us that time is more like space than we thought, but it does not by itself settle questions about determinism. Another response is that our subjective experience of time flowing, of making choices, of the present being special, is compatible with the block universe view. If we understand these as features of consciousness, rather than features of objective physical reality, consciousness experiences events sequentially along a world line through space-time, creating the sense of flow and the perception of a moving present. This experiential flow is real and important for understanding human consciousness, even if it does not correspond to an objective division of space-time into past, present, and future. We are four-dimensional world lines through space-time, and our consciousness experiences these world lines one event at a time, creating the perception of temporal flow. These questions show how physics connects to philosophy, how discoveries about the physical structure of the universe force us to reconsider metaphysical assumptions we might have taken for granted. The constancy of light speed, by forcing a radical restructuring of our concepts of space and time, inevitably affects how we think about existence, reality, determinism, and consciousness. Physics cannot answer these philosophical questions definitively, but it constrains the space of possible answers and reveals which intuitions are reliable guides to reality and which are artifacts of our limited everyday experience. Looking toward future developments in physics, the constancy of light speed will continue to play a central role. In quantum gravity, physicists are attempting to reconcile general relativity's description of space-time curvature with quantum mechanics' description of matter and energy. Various approaches, string theory, loop, quantum gravity, causal set theory, and others, all must preserve the constancy of light speed as an emergent property at macroscopic scales, even if they modify space-time structure at the Planck scale, where quantum effects become important. Any successful quantum gravity theory must reproduce special and general relativity in the appropriate limits. String theory, for example, describes particles as tiny vibrating strings in a higher dimensional spacetime, but it must preserve Lorentz invariance and light speed constancy in the four familiar dimensions. Loop quantum gravity quantizes spacetime itself, describing it as a network of discrete quantum geometries, but it must reproduce smooth spacetime and constant light speed at large scales. These theories represent different approaches to quantum gravity, but they share the requirement of respecting light speed constancy in domains where we have tested it. There is speculation that at extremely high energies or short distances beyond what we can currently probe, light speed might depend slightly on photon energy, with different wavelengths traveling at infinitesimally different speeds. This would indicate new physics beyond general relativity, perhaps related to quantum gravity. Observations of gamma-ray bursts from distant galaxies provide some constraints on such effects. High-energy and low-energy photons arrive from these bursts at very nearly the same time after traveling billions of light-years, suggesting their speeds are equal to extraordinary precision. But even better measurements might someday detect tiny energy-dependent variations that would revolutionize our understanding. So far, no such variations have been confirmed. Another frontier where light speed constancy becomes important is in attempts to unify all fundamental forces. The electromagnetic, weak nuclear, and strong nuclear forces have been partially unified in the standard model of particle physics, but gravity remains separate. A complete unified theory would need to explain how all forces arise from a single underlying framework, and any such theory must respect the constancy of light speed built into special relativity, grand unified theories and theories of everything. Attempt this unification, but none have yet succeeded in a fully satisfactory, experimentally confirmed way. The constancy of light speed remains a fixed point that any successful theory must explain and incorporate. In practical terms, future space exploration and technology development will need to take relativistic effects into account, more and more as we push to higher speeds and greater precision. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.